The Johns Hopkins Science Review, presented by the Johns Hopkins University and WAAM in Baltimore. This is the Johns Hopkins University, famed for 75 years for its contributions to science and the humanities. Here in its many laboratories, Hopkins scientists are constantly probing into the still unknown secrets of science, which, when discovered, will be translated into benefits to be enjoyed by you, the people of America. Each Tuesday night, we catch a glimpse of the results of their research. Tonight, we present a special program of the Science Review's Highlights in Review. Here now is Lynn Poole of the Johns Hopkins University to introduce tonight's program.
Good evening, ladies and gentlemen, and welcome to another Johns Hopkins Science Review. I want to tell you how much we appreciate the letters that you write to us and what you have to say about these Tuesday night programs. Now, many of the letters that we receive are asking for a repeat on programs that have been done in the past. Just a few days ago, I received a letter from someone up in New York asking that we redo the program, Don't Take Your Heart for Granted. And just this morning, a postcard came in asking if we could do Troubled People Meet. Now, your nice letters come because you've seen the programs and like them. You've also asked that we repeat some of these programs because you missed them, or friends have told you about them and you would like to see them. Unfortunately, that's not possible for us to redo all these programs, so in planning this program tonight, we decided to do the highlights from the programs that we have been doing through the winter. Now, if some of you will remember, last fall we did a program dealing with heat and cold, and some of the research being done by scientists in this field. And from the low-temperature laboratories at Johns Hopkins University came the story of freezing the atom.
Atoms are the smallest particles known to man. They make up molecules, which in turn make up matter or substance. These atoms are in constant motion, and because of this motion and the resulting friction, heat is produced. When atoms of a substance are speeded up, the substance becomes hot. But when the atoms are slowed down, the substance becomes cool. If the atoms are stopped altogether in a substance, it will have a temperature of 490 degrees below zero.
Let us now see again what the results are when atoms of a substance are slowed down. To slow them down, we will use liquid nitrogen, which has a temperature of 330 degrees below zero. It is so cold that it is now boiling violently from the heat of this table which it is sitting on. With the liquid nitrogen, we will first slow down the atoms of this ordinary piece of rubber tubing. As the tubing is placed in the liquid nitrogen, it causes the nitrogen to boil even more furiously. Now the piece of tubing is frozen and has about the same texture as glass. When we strike it with a hammer, we see it shatter.
We will now pour some liquid nitrogen into the glass container. And the same thing will happen to a bite of chocolate ice cream. It freezes instantly into a lump that is almost as hard as steel. If you were to put this in your mouth, your tongue would more than likely assume the same texture and break off. And now the ice cream will also shatter like glass. You can see that freezing the atom provides a great many entertaining demonstrations. However, it does more than this. The low-temperature research carried on at Hopkins has brought about the development of the bolometer, an instrument which enables man to see objects at great distances, even in fog or darkness. An instrument of proven value, both in war and peace. Later on in our science series, we explained the workings of another instrument which benefits every one of us every day. It was the vacuum tube, showing electrons at work. This simple vacuum tube makes possible all types of communication: telegraph, telephone, radio, television, and even the electricity which you use for the everyday appliances in your home. This, very briefly, is the principle behind the vacuum tube. In the tube, there is a piece of wire which becomes red hot. When this wire becomes hot, it throws off electrons inside the tube. It throws off electrons just as the particles of puffed wheat in a jar may be blown up into the air by a blower in the bottom. The electrons then go to the plate of the tube, just as they are now striking the sides of this jar.
As a result of this action, the tube is capable of turning alternating current into direct current, or to act as an amplifier. Vacuum tubes are now changing alternating current to direct current in our transmitter, and they are now amplifying our signal so that you can see and hear this program. It does this by controlling the electrons which come from the hot wire through the grid of the tube.
If there are a lot of electrons flowing from the wire to the plate, you have a bright picture and normal sound. But if we cut down on the flow of electrons in the tube, the picture becomes dim. Watch closely while we cut down the flow of electrons in the tube of your set. We are cutting down the electron flow now, and your picture is getting dimmer and dimmer. Now, as we increase the flow again, the picture on your set comes back to normal.
You can readily see that without this mighty midget, you could not see this program or use any of the electrical conveniences you now enjoy. In the month of December, we felt that we should answer some of the questions which our audience has been kind enough to send in. A highlight of this program was an explanation and demonstration of atomic chain reaction.
Atomic chain reaction is simply a process of knocking the atoms of a radioactive material off balance. For example, if a neutron is shot into an atom of U-235, this atom becomes very unstable. Because of this instability, the U-235 atom breaks in two, forming two more neutrons. These neutrons, in turn, hit two other U-235 atoms, causing them to break up. Then the neutrons from this fission hit four atoms. This continues on and on, doubling each time. This is nuclear fission, or chain reaction. When this happens, there is a tremendous release of energy, so much that it can cause a terrific explosion, or perhaps drive a rocket to the moon.
Atomic chain reaction can best be demonstrated by this arrangement of mousetraps and sugar lumps. Each mousetrap is baited with 2 lumps of sugar. Now, let us imagine that the lumps of sugar represent neutrons. When other lumps of sugar are thrown in on a mousetrap, it throws off 2 lumps, which in turn cause 2 other mousetraps to throw off 4 lumps, and on it goes. A very simple chain reaction. Watch now as we add some foreign lumps of sugar, and you will see the chain reaction.
In the month following, the Johns Hopkins Science Review did a program dealing with the unbreakable laws of the universe. Physical laws which govern all things were discussed and demonstrated. The law of inertia, the law of action and equal reaction, the law of the conservation of motion, the law of gravity, and the law of atmospheric pressure.
According to the last law, air has a certain weight. Because of this, the air stacked up on top of us exerts a pressure on everything of about 15 pounds per square inch. This doesn't seem like too much pressure to us, since there's the same amount of pressure inside our bodies and inside all other things equal to the 15 pounds per square inch. However, if this pressure inside an object is removed, the outside atmospheric pressure shows itself by immediately crushing the object.
This can will perfectly demonstrate the law. The can has been sealed off so that there is only one opening. This opening is connected to a vacuum pump. Now, as the pump begins to draw the air out of the can, we see the tremendous forces of atmospheric pressure crushing the can. This is an unbreakable law of the universe.
One of our most touching programs was the one which told the story of the fight against polio. To do this story, it was necessary for us to go to the polio hospital with our film unit and record on film the work being done to restore polio victims to a normal, useful life. Our aim for this was to demonstrate for you some of the techniques of restoring strength to the damaged muscles of polio victims. Let's look again at some of the film which we took at the Children's Hospital here in Baltimore.
This is the exercise room at the hospital. Here the therapists help the patients manipulate the muscles and nerves in the patient's arms and legs in order to help the patient regain the control and use of polio-stricken muscles. Here you see a young lady receiving a heat treatment from lamps under the hood over her legs. Beyond is another young woman whose leg is being exercised by the nurse. And in the center, is a young man in braces who has had treatment and is now learning to walk. As a matter of fact, the day we visited the hospital, he was walking for the third time.
It was a thrilling sight to watch the doctors, nurses, and therapists working patiently day in and day out to restore the victims of polio to normal life, and to see the courage of the victims themselves in their fight against polio.
The Johns Hopkins Science Review not only tells about scientific advances, but it also occasionally gives advice. It did so when it said, "Don't take your heart for granted." We told what the heart is, what can happen to it, and how to take care of your heart.
The heart is a double pump. It is divided into the left and right side. Blood is pumped out of the left ventricle into the arteries, which carry it through the aorta to the head, extremities, and all organs of the body.
In these organs, the blood gives up the oxygen which they need and takes in its place the carbon dioxide, which is a waste product. The blood then returns through the veins to the right auricle, which is a reservoir to collect it.
When the auricle is filled, the valve closes. The auricle contracts and fills the right ventricle. The ventricle now contracts. This valve between the ventricle and auricle closes to prevent backflow, and the heart, acting as a pump, forces the blood through the pulmonary artery. The blood now passes through the lung where it gets a new supply of oxygen. Back from the lungs through the pulmonary veins, the blood reaches the left auricle. From there to the left ventricle. Then the blood begins again the circuit to the arms, legs, and organs. This occurs over and over again, normally at a rate of about 80 times a minute.
Many things can go wrong with this marvelous piece of machinery. For example, a heart may be deformed in such a way that the good blood from one side is polluted by the dirty blood in the other side. This cuts down the oxygen supply to the rest of the body, and the result is the blue baby. Rheumatic fever may cause damage to the heart valve so that blood leaks backwards when the heart pumps. This means that the heart must do more work than is normal, and so it must enlarge. This can lead to heart failure.
Again, the veins which feed the heart may become hardened and prevent the heart from getting enough nourishment. When this happens, the muscles of the heart cannot function properly. This is coronary thrombosis. Right now, scientists at Hopkins and all over the world are working on preventives and cures for these heart conditions. In some, they've been successful, but in others, they are still far from the answer. We gave the advice to take care of your heart. Don't overwork it. If you want your heart to go on pumping for many years to come, don't take your heart for granted.
Archaeology, Key to the Past, offered an interesting half hour. On this program, we demonstrated how the archaeologists are able to uncover the remains of ancient peoples and assemble them into an accurate history. We gave as one example of the archaeologists' work, the lost civilization of the Etruscans.
The Etruscans were a people who lived in what is now called Turkey, but who later migrated to central Italy. For hundreds of years, nothing was known of these people. Then archaeologists began finding some of the remains of their nation.
From these remains, a fairly complete history of the Etruscans has been pieced together. By studying the pieces of evidence, the archaeologist is able to learn many things about the Etruscans. This vase tells the expert that the Etruscans had a great sense of form and style, and that they had a very unusual method of firing pottery, which no one has ever been able to duplicate.
Figurines such as these indicate that the Etruscans were great warriors and that they concentrated on military power in their early days in Italy. The Etruscans were conquerors when they went to Italy, and they ruled and policed the land with their army.
Later in the history of the Etruscans, as they suffered great military defeats at the hands of the Greeks and the Gauls, Laza, goddess of fate, became more and more prominent in the life and art of the Etruscans. And their paintings showed that as the civilization declined, the Etruscans showed a growing concern over death and the afterlife.
And so we see how the archaeologist slowly and steadily adds to our body of written and intelligible histories. Through his work, we are helped in an immeasurable degree to know our common past and our common heritage. Truly, archaeology is the key to the past.
Not too long ago, we did a program which dealt with our future. From the laboratories of Johns Hopkins, researchers in the field of cancer came into the studios to show us the basic research which is being carried on in cell growth. This program gave us the opportunity of seeing cancer cells in action. Listen now while Dr. Guy tells us about the growth of cancer cells.
How the normal cells, when properly injured in the body, change to cancer cells is still a mystery. Normal cells and cancer cells, studied separately outside the body, permit us to learn how different they really are. These greatly enlarged living photographs of flattened cancer cells on the left and normal cells on the right show us some of the differences between them. In the scenes that we are now watching, we see chromosomes containing the hereditary units of the cell as they jockey about before the cell divides. These chromosomes must be in an exact position in order that they may split longitudinally and thus reveal to you the mechanism of cell division. In the very center, you will soon see these chromosomal masses parting so that the cell may separate into two daughter cells. Watch closely now, and you will see the longitudinal splitting of these chromosomes and the formation of deep fissures as this dividing normal cell splits into two normal daughter cells. Here they go. Watch the cleavage furrow spread down through the normal cell as two new daughter cells are formed. Shortly after their formation, they will continue to grow in normal fashion. In the following scene, you will see a large cancer cells. Cancer cells in general are larger than normal cells, and here we see one again, jockeying its chromosomes, containing hereditary units now in greater number, as these chromosomes separate to form not two cells, but three cells, as you will see here, one much larger than the other. This is an abnormal type of cleavage, so common in cancer cells. In the scene, one can see the thinned out portion of a cancer cell as it takes in particles from the medium and rapidly discharges other parts. This activity is speeded up well over 100 times and reveals to us the internal traffic of a cell at an exceedingly high magnification. By studying such living cells, we hope to learn much about the behavior of the protoplasm of these living cells taken from animals and also taken from humans. In the succeeding scenes, we will show you some scenes of portions of human cancer cells. And here we have one taking in large droplets much more rapidly than the process as seen in a normal cell. These droplets are transported to a kind of digestive center where the cell can utilize the materials that it needs. In the succeeding scene, we will see the rapidly moving protoplasm in a cell which is greatly magnified, so greatly magnified that we could convert this image into an electron image and there study the structural organization of a human cancer cell.
Many people were puzzled when we presented a program about science in art. What does art have to do with science? Science and art have a lot in common, as some of you may remember.
The work of cleaning an old painting is a skilled science. Here is a painting by the Frenchman Sisley. One side is dark, dingy, dirty, yet the other side is bright. This painting is half cleaned. Why did it need cleaning? Well, originally, the entire painting glowed with fresh, bright colors. But one day, the colors grew dim, so someone put a coat of varnish on it to make it bright. It became dirty again. Another coat of varnish was applied, until the successive coats and dirt had completely obscured the painting. The art of restoring the painting is a painstaking one.
One of the most rewarding examples of scientific restoration was performed on this 15th century Spanish painting. Lest one think that the work is done quickly and without difficulty, look at this painting, which had been ravaged by time and weather and was found in this deplorable state. Carefully notice the eagles on the voluminous skirt. These did not belong there. They had been painted on many years after the original painting was completed.
The back of the painting was cracked and covered with dirt. Heat, rain, and humidity had warped this panel until the whole painting had been pulled out of shape and was unfit to hang on the wall of a museum. Because of this, a great art treasure was about to be lost until scientific restoration was performed. And one day, this lovely painting emerged in all its original beauty.
Today, due to the care of restoration, the bright colors can be seen. The cracks, damage, and dirt are gone, as are the eagles on the skirt, which we saw in the first view of this painting in its damaged state a moment ago. Those eagles had been painted on by someone long after the painting left the studio of the original artist. In addition, the polychromed and gilt wood, creating an effect of an altar around the Virgin and Child, have been cleaned and restored to their original luster. They frame the scene, creating a power and majesty around the serenity of a mother and her child. This painting can be seen today at the Walters Art Gallery in Baltimore.
Another example of science and its ability to bring back the original beauty of paintings is this portrait, well known to every adult and schoolchild in this country. Painted by the famous Bostonian Gilbert Stuart, the canvas was poorly preserved. It was grimy and had to be touched up by a later painter. Again, restorers at the Walters Art Gallery went to work. And now this famous painting of the father of our country is restored to its former bright color. A dynamic, forceful, and vital painting. A painting befitting the ability of Gilbert Stuart, the painter, and the strength and genius of George Washington.
This painting by Fontormo, famous Italian painter, hung in the Walters Art Gallery for many years after it had been brought to this country, until one day our guests and their colleagues looked at it with a very critical eye. They began to wonder if there was not something wrong with the heavy painting of the heavy skirts of the lady you see here. It bothered them for some time, so they took a closer look with ultraviolet light, then with X-ray, and they found the head of a curly-haired, tow-headed young man hidden beneath the thick black paint of the mother's skirt.
This young man's head had been painted out long after the original painting had been produced. So Miss Packard and Mr. Kirby gently began the process of chipping away the paint which had covered the young man. And they found his small hand tightly grasping the hand of his mother. Working across the canvas, skillfully removing dirt, paint, and varnish, the entire painting was exposed to view. At this point, it was found that the original paint had been damaged, so it was necessary to restore pockmarks on the canvas, treat the canvas, and subtly match the colors of the original with carefully prepared pigments.
This was a tedious job, but it is worth it to the restorers when they walk through the Walters Gallery today and see groups of people standing in front of this painting, enjoying its beauty. Here is another example of the work of science, which contributes much to the pleasures of our daily living.
These have been some of the highlights of the Johns Hopkins Science Review that has been presented throughout this winter. Others of you will remember other programs that we've done on Tuesday nights. Our winter series last October 3rd started with a program on fear, the psychology of fear and the physiology of fear. What happens to us when we become afraid and how can we overcome this fear? Many of you will remember the program on X-ray, the super sleuth, when we introduced for the first time a miraculous new X-ray developed at the Johns Hopkins Hospital by Dr. Russell Morgan, which is engineered along television lines. At that time, we had probably the first consultation and diagnosis by 3 doctors, widely separated, one in Chicago, one in New York, and one here in Baltimore. And to remind those of you who have written to us and asked us for programs, you may remember the program on stream pollution, how streams are purified along factories. And another program in the same category was a program on how water is purified. Then the U.S. Public Health Service, the National Institutes of Health in Bethesda, Maryland, gave us a very exciting program on schistosomiasis, the killer. That disease that affects 115 million people throughout the world. A disease that is being brought under control by our U.S. Public Health Service in coordination with their colleagues in other countries. And a few weeks ago, we presented Dr. Arthur K. Parpart, who demonstrated for the first time to a large audience his magnificent microscope, a microscope through which no human eye appears, but the television camera looks through it and shows you things never before seen by men. Now, as you are about to go on your summer vacations, we're going to be here every Tuesday night. But the people that have been working on this program are about to have their vacations too, and a very well-earned vacation it is. And at this time, I would like to thank the men who are behind the scenes on the Johns Hopkins Science Review. The cameramen that are here every Tuesday night to bring you these pictures. The floor manager that keeps things going in the studio. The audio and the video men. And the engineers that put the program on the air. We owe them a great debt of thanks, and we want to acknowledge that thanks. And we hope that most of you will be with us next Tuesday night when we begin our summer series, when the Johns Hopkins Science Review presents a report to the living.
Next week, the Johns Hopkins Science Review will give a report to the living. The story of how ACTH saved the life of young Dickie Wood. You will see Dickie, his parents, and the doctors who treated him, reenacting the roles that each played in this real-life drama. Dr. C.J. Van Slyke, director of the National Heart Institute, will be the guest scientist. He will explain the development, clinical experimentation, and the medical uses of the new wonder drug, ACTH. Be with us for Report to the Living.
The Johns Hopkins Science Review is produced by Lynn Poole. Associate producer, Sterling Reynolds. Directed by Ed Sarrell. Associate director, Ken Kelty. Art director, Barry Mansfield. Tonight's announcers were Joel Chaseman and Ted Jaffe. Portions of this program were mechanically reproduced. The Johns Hopkins Science Review originated in the studios of WAAM.
This is the DuMont Television Network.